All right, picking up from the last video, we want to wrap up the hypergeometric distribution with our manual operations. As I said previously, Excel is more handy, more useful, but it is sometimes beneficial to go through the long math to calculate the probabilities, the mean, and the standard deviation in order to get a sense of what Excel is doing. Let's say we have this situation down here. 3 different computers are checked from 10 in the department. 4 of the 10 computers have illegal software loaded. What is the probability that 2 of the 3 selected computers have illegal software loaded? To calculate this, we're going to use the formula here. And let's just plug in the numbers up here. We have the probability of 2 computers having illegal software is equal to, now this terminology is, it's not fractions. If these were fractions, you would have a line between r and x, between the numerator and the denominator. These are actually the denotation for combinations. So this means r elements taken x at a time, so on and so forth. Well, what is R? R is the number of elements in the population labeled for success. Well, we know from down here that there are 4 of 10 computers that have illegal software. So 4 is the number of elements in the population labeled for success, because success in this experiment is illegal software. Okay, so we're going to put 4 here. And our x value is, the little x, is the number of successes. And that's going to be 2. 2. So what this means is how many combinations are there of 4 elements taken 2 at a time. Right, let's continue on. Let's plug in here capital N minus little r. Well, capital N is the number of elements in the population, and we established that there's 10 computers in the population, the 10. We subtract from that R. Okay? That's the number of elements labeled for success, and we established that that's going to be 4. And then we have little n, which is the number of trials. We know that's 3. That's our sample. And we're going to subtract from that x, which is 2. And then our denominator is going to be the capital N, number of elements in the population, which is 10, and little n, which is the number of trials. And that is 3. So that's how we set up the formula. Once you do that, you can find these values. You do it on a calculator, you can also do it in Excel. So we'll use Excel as our calculator. So we're going to put equals combination. And we want to pull up the argument box here. For this first one, we're going to pull 4 elements 2 at a time. So 4 is the total number of items, and 2 at a time. And it actually gives you the result down here, so we can just go ahead and write that in. So we have 6. Okay. And then for the next one, we need 10 minus 4, so 6 elements, 6 total items, taken 3 minus 2, 1 at a time. And that gives you 6. So 6 times 6 in our numerator. And then our denominator is going to be 10 elements taken 3 at a time. And you get 120. So that's 36 over 120, which is going to equal, if you want to use Excel for your math, 36 divided by 120 and you get 0.3. Okay, so that becomes the probability of getting two, pull this over here, getting two of the three selected computers having illegal software. Okay, now let's calculate the mean of this problem. And to do this, we're going to use the formula. Remember, the mean is also the expected value. Little n is our sample size. We already established that we drew 3 computers from the 10 in the larger population. So it's 3. Okay. And we're going to multiply that by little r, which is the number of successes in the population, over capital N, which is the number in our population. Well, the number of successes in the population are 4, right? And there's 10 computers in the population, right? 4 of 10 have illegal software, so 4 over 10. And if you do this correctly, you will get 3 times 4, which is 12, divided by 10 is 1.2. That is the mean. This distribution would have an average value, an expected value of 1.2 computers that have illegal software. For the standard deviation, we just plug in the numbers here. Let's move this over a bit. And actually, let's do it right here so we can see the narrative. Well, we have for our sample, we know that's 3. We're going to multiply that by the number of successes in the population over the total population number, which is 4 out of 10. Of course, this is what we just calculated, 1.2. We're going to multiply that by 1 minus the successes in our population over the total population. And we're going to multiply that by the numerator here, total population minus the sample population over the total population minus 1. If you do this correctly, you will get the square root of 1.2, like this, times 1 minus 4/10, which is 1 minus 0.4, which is 0.6, times, looks like 7 over 9. 7 over 9. So we're going to need to use a calculator for this. Sometimes you can do these in your head, but let's pull up Excel and use it as a calculator here. I'm going to put equals, and we're going to have the square root of 1.2 times 0.6 times 7 ninths. Okay. And you should get 0.748. About 0.75. Okay, now if you wanted to do the hypergeometric formula in Excel, maybe you want to do this to verify that the probability you got up here is correct, then we can do that. Okay, let's pull up Excel here and look at our problem. We're going to, in the first column, put the possible successes, essentially our x values. If we draw a sample of 3, we can get 0 successes, 1 success, 2 success, or 3 success. Then we're going to put the hypergeometric formula. We want to select the correct one, and let's pull up the argument box here. The first cell is the successes in the sample. Well, that's going to be our columns here, or column A. And then in the next box, we're going to put the size of the sample. Well, we know the size of the sample is 3. Then we're going to put the successes in the population. Well, we know it's 4. And we're going to put the size of the population, which is 10. And we don't want a cumulative distribution, so we're going to turn that off, false. And now you've got that. Again, use percentages and round, say, to the 10th. And we drag this down. And remember, we calculated the probability of two computers being selected having illegal software. And we got 0.3 with our manual computation. And look at that. We have 2 equals 0.3 or 30%. Same thing. Right? So this is a nice way to verify your results. You could also create a graph here if you wanted to, right, to illustrate the respective probabilities. And go to Insert, Charts, Column. And of course, we have to select our data so that we get the zeros down here. So we want to select data, horizontal axis. And now you have a probability distribution. Okay, the last thing I want to do is revisit an application we talked about in a prior video when we did the binomial analysis. And the reason we can now revisit this is because at the time we hadn't developed the hypergeometric yet, so we couldn't really finish or accurately answer this question. Let's read through it. It says 40% of a school's population is female and the entire school has 30 students. You randomly select 10 students to attend a lecture on industrial statistics. Okay? Using Excel, create a probability distribution table and graph. Based on the results, what is the probability that exactly 6 of them are female? What is the probability that more than 6 are female? Well, we did this with the binomial and then realized it's not right. So let's use the right one. And we're going to do the same thing except with the hypergeometric formula. So our first column is going to be the number of successes, and if we're pulling 10 students, we could have anywhere from 0 to 10 successes. So drag this down, and then we're going to put the hypergeometric distribution, and let's pull up the argument box. The successes in our sample would be the first column. The number in our sample, well, it's 10 students. The population success, this needs to be derived. But we know if the population has 30 students and 40% are female, then 40% of 30 is 12. So population successes are 12 of the 30 students would be female. Number in the population would be 30. And then cumulative we don't want, so we put 0. Now we drag this down, and you get your hypergeometric distribution. We could graph this. And take this, insert, column. We know how to do this, so I'm going a little faster maybe than what we've done before. We're going to select data, modify our horizontal axis, and there we go. So that gives us our hypergeometric. Okay. Now, if we wanted to, we could compare this to the binomial. Let's create the next column, but we're going to put binomial distribution. Same process, right? We're going to have the number of successes represented by our first column. We know the trials, there's 10, right? That's our sample. Probability of success is 40%, so 0.4, and we don't want cumulative. And if you percent this and then round it to the 10th, drag it down, you have your binomial. We could graph that. And what's nice about doing this is we can compare the two. And you're going to see that there's not as much of a difference as you might think. There is a difference though, and only one is really accurate, the hypergeometric, because of the nature of the problem. Okay? So this is your binomial. So the probability of getting exactly 6 females is 9.4%. To get the probability of greater than 6 females, you would simply sum the probabilities of 7, 8, 9, and 10. And you can do that on your own. Thanks.